here comes the item that we want to discuss today. So probability and statistics. So you may hear of these terms and vocabulary a lot, but let's try to formally define them first. So probability is a mathematical language for quantifying uncertainty. So we want to do some decision, we want to make some choices. Where decision and choices, they are coming with some uncertainty. We want to measure and quantifying them. So basically this uncertainty represents a chance, likelihood, or degree of certainty, just the same word. Where chance or likelihood of some event will occur. So this is the most general notion of probability. And not only that, depending on the method of measurement, sometimes you want to come up with a distribution of the probability, distribution of the chance of the event. On the other hand, statistics are more concerning with handling data using different analysis technique and collection or generalization techniques. So probability is a mathematical language or mathematical tool, and statistics, it's not really formal definition, but let's just talk it informally. So this is more like discipline or more like methodology. But they essentially, sometimes they are even used interchangeably. So the difference is really subtle. So the third point is actually saying that they are closely related. But still, there are some differences. So in terms of probability, we are concerning with this kind of problem. So you have a fair coin, and you want to toss it 100 times. And you want to calculate the probability of seeing heads more than 60 times. Well, if you see similar problem in the statistics point of view, you have a coin and it has some property, but the property is unknown. So you don't know the tendency of head or tail of this coin. But given that, you want to investigate by doing some experiment. So you want to toss it 100 times. So you counted the times of head, and based on the observation, you want to use probability to draw out the conclusion. So, this is my experiment. Out of 100 of times, I saw head 60 times. So from here, maybe I can come up with some conclusion in terms of the probability. So we are basically dealing with the same problem, but perspectives are slightly different. Brief history. So probability came from the study of gambling and insurance, and from 17th century. And statistics, it is from long ago. So this is actually from the Bible. So 민수기, where the counting population, and that can be an example of statistics. So it was from really, really long time ago. But the main methodology was developed within 100 years. So that's an interesting point. But anyhow, probability, in a simple term, a quantity of likelihood assigned to an event. So there will be an event. So from probabilistic experiment, we are going to play with these terms. So one is experiment or trial, where you are running some kind of a test multiple times to collect data or collect observation. And for that, you have sample space. So this is the domain of the observation. So from these possible value, I will see the outcome, something like that. So that is defining sample space in statistics. And the variables, while we are making observation, while we are doing some experiment, the variables are called as event. So thinking about twinkles, the sample space is head or tail, and an event is one single event or a series of events. It could be. We're tossing a dice, where sample space is 1 through 6, and event, if you want to find the event where the number is even, where your event could be 2 per 6. And we talked things in terms of statistics, so event, experiment, and trial, sample space where these were sort of terms that you may want to have when you measure probability. But the main thing we pursue is some value, and we call that as a random variable. So where we have variable and we want to model that with probability. So in essence, where from sample space there is a variable defined. For example, if we have this coin tossing event where possible value is 0 or 1, where one is head, the other is tail, and there should be a variable that can accommodate this possible value, and we call that random variable. So from now on, we are going to play with this random variable, putting the probability in front of it, sometimes the likelihood of X or something like that. So here comes some simple example. We're playing with the probability. We're given two 6-face dice. The probability of rolling 7, where there are 36 different combinations if you roll 2 different dice. And out of 36 different combinations, these are all possible combinations that make 7. So you simply count all possible number of events and divide it by 36. And this is your probability. So this is something we have done from the middle school, so straightforward. And again, you have two 6-face dice, and the probability of having 7 or 11. So here we have or. In this case, we consider all possible cases making 7 and all possible cases that rolls 11. So there are 2 more cases on top of the previous cases that we sorted out. So we have total 8 possible cases that makes 7 or 11, and divided by 36, that will give you the probability. Well, here or is we call as conjunction. So when you have conjunctive form, where we calculate the probability for 2 different cases, so probability rolling 7, probability rolling 11. Calculate these 2 individually and simply taking the sum, and you will get this solution. And moving on to different example. So you have given box of 15 chocolate, and out of them 5 dark, 5 milk, and 5 white. And you want to pick only one of the chocolates. And what is the probability of getting dark or milk? So this is the question. And again, you have or in between. So this is a conjunction. In this case, you want to calculate the probability of getting dark, probability of getting milk, and taking the addition of them. So taking the sum, and this is your probability. Given a box of same condition, so 5 dark, 5 milk, 5 white, and you want to pick 2 pieces of chocolate. And the probability of picking the same kind twice. So at first, well, you have freedom to choose anything, right? So you can pick any of 15. So initial choice, basically you are picking one, so basically probability is 1. So whatever you do, it counts. And then you will choose one of dark or one of milk and one of the white. Well, there is actually my mistake. So you have picked one. So you have 14 chocolate pieces left in the box. Out of them, you want to pick the same color. So it's going to be, well, 4. So eventually your probability is 4 over 14. And this is a more combinatorial problem. So here you have 2 jars. And in these 2 jars, you have 12 marbles. And well, those 12 marbles are distributed randomly. So 5 of them are green and 7 are yellow. And in the red jar, you have 5 yellow, 2 green. In the blue jar, you have 3 green, 2 yellow. And from outside, you cannot see the inside of the jar. So you pick one marble and look at the color. Well, that's the game. So given that, well, let's say the probability of picking red jar is 0.3. That means the probability of picking blue jar is 0.7. Given that, you want to calculate the probability of getting green. So probability of getting this guy, probability of getting this guy. Well, from each jar, you can easily come up with that probability that is, 7 out of 2 and 3 out of 5. And you want to associate the individual probability for getting jar. So 0.3 multiplied by 2 out of 7, 0.7 multiplied by 3 out of 5. It will give you the probability. So these problems were sort of warming up for your brain. And let's move on to more conceptual thing and more principle stuff. So we talked about sort of playing in terms of probability. And we were essentially talking about distribution and density in terms of random variable. But we were only focusing on the probability of getting that random variable. But behind of it, we were actually building this kind of thing. So behind of our discussion, we have the notion of a probability function. And there are multiple types of probability function. So one of them is probability mass function or probability density function. So first guy, probability mass function or PMF, this is for discrete random variable. Well, thinking about dice tossing, so you have 1, 2, 3, 4, 5, 6 different output. So you want to count on what you observe. So maybe you have seen 2 times, 5 times of 2, or 2 times of 3, 3 times of 4, 6 times of 5, 5 times of 6. Well, this is each defining a probability space, and a generalization of such is a PMF. So based on this PMF, your probability could be calculated or modeled. For example, where say you have a probability term P of K. So you have a random variable K, and it could be one of the value that K is defining. And let's say that probability is defined in terms of this combinatorial format. Well, in this case, if you draw the same, the actual outcome of this calculation, where you can see this kind of distribution. So actually, this is a known distribution called the multinomial distribution. And this exact example is specifying that you have 10 trials of a coin toss. And this coin is biased, so you may see 20% of head and 80% of tail. And you do coin toss 10 times, and this is the probabilistic distribution, how many times you will see head eventually. So with this probability, you will see 0 head. With this probability, you will see 1 head. With this probability, you will see 2 head, and so on. So what we have discussed in lengthy sentences, it can be summarized in a simple notion using this combinatorial format. And this guy is defined by multinomial distribution. So today we want to focus on what is a probability mass function. So probability mass function is for discrete random value. Let's move on to probability density function. So PDF is for continuous random variable. And this bell shape is somewhat very familiar to us. So this is a normal distribution. But given that we want to calculate the probability of my variable becomes a value within A and B. And calculating such a probability where I have given a probability density function that looks like this. So this is my PDF. And given that here is A and B, essentially calculating the probability is measuring the area in between. So PMF is defining the entire probability distribution, and well, the idea of getting probability out of it is measuring the area. So that is PDF. And here are some additional constraints for probability. So these are the condition for a number to be a proper probability. So probability value should be always larger than or equal to 0. So there is no negative probability. And there could be multiple possible values in my sample space. So if you consider all possible values and their probability, well, the sum of individual probability should be 1. So well, that was when your variable space is discrete. And when your sample space is continuous, you may want to use integral. And the third condition, well, if you have disjoint event, so you have a dice, and this single dice cannot be 1 and 4 at the same time. It should be only one number, right? So, well, you have 6 disjoint event with a single dice. It can be only one number at one time. It cannot be 2 different numbers at the same time. So, well, if you consider this kind of disjoint event, well, if you take the sum of those probability, well, if you take the sum of those probability, that is considering the probability of union of all events. So when we are modeling probability, we are either modeling probability mass function or probability density function, depending on the variable type. And let's move on to CMF and CDF. So CMF is a cumulative mass function. And again, this is a mass function. So this is for discrete random variable. So it can be defined in this way. So within my sample space, each of these sample value has some probability value associated with each. And otherwise, so any value other than my sample space, it will result in 0 in terms of probability. So here are some more concrete example. So in the previous slide, we talked about PMF. So if we have a PMF like this, when R is 0, my probability is a quarter. And R is 2, my probability is 3 quarter. And it can be represented by 2 bars like this. And this is PMF. And we are talking about CMF. And CMF is the accumulation of PMF. So if you're taking the cumulative form, so well, initially it is 0, and you meet with 0, it will jump to 1 quarter. And it stays at the same level. And when you meet 2, it jumps up to 1 because well, you're adding the probability of this guy and this guy. So well, you're accumulating the probability along with the sample space. That is the idea of CMF. And let's talk about CDF. So it's density coming to the distribution. So CDF is short for cumulative distribution function. And that is for continuous random variable. So speaking of the same Gaussian function, well, normal distribution, CDF is defining all the area up to some point. So I want to estimate the probability of getting my variable smaller than or equal to a specific value. So well, this blue line again, PDF of normal distribution. And if you take the cumulative form of the normal distribution, you will get a CDF like this. Well, one thing you should notice is the ticks are different. So this blue line tick is ranging between 0 to 0.08. So it's really, really small. and you're accumulating that, and this red line, this red curvature is ranging between 1 and 0. So if you think about CDF, it should be always ranging between 1 and 0. If you accumulate all the probability, it should sum to 1. And let's move on to some common notation. So random variable sounds important to us. So random variable capital X, it takes the value, the actual observation, usually coming in lowercase. And we use both terms, so the variable and actual value in probability notation as well. So probability of variable X should be a certain value. We notate things in this way, but this is wrong. So we use this short form quite commonly. But when you see a small value here inside of the parenthesis, that is actually representing my variable value is equal to some specific value. And for continuous random variable, for PDF, where we cannot say a value at specific point because it does not have width. So where you cannot measure the area without width. So we need to define the width in terms of ranges. So the ranges is given, so A through B, and that is actually representing the integral. So that's basically we're specifying what we are defining, what we are playing with.